when we discussed the different types of forces that can be acting on an object, one particular force that we talked about, we introduced, was the frictional force. And we also mentioned there are two types of frictional forces, one being the force of static friction, and the force of static friction prevents an object from sliding on a surface. So in this sketch right here, you're looking at a person trying to push a box, and suppose the box is at rest and not moving. Then we know you've got and if I were to ask you to draw a free body diagram for the box, so here you're looking on the right, you are looking at a free body diagram of the box. And there is the pushing force that the person is exerting. So let me call that F push, and this is exerted by the person. And well, let's start also finish up with the vertical forces. You got the weight acting that in the downward direction. There is, and this is the object responsible for that is the earth. Always get into the habit of including this as well, which object is exerting the force on the box. And you have the normal force acting up this way, and that is the force that the floor exerts. It's the vertical force that the floor exerts on the box. Now obviously, since this box is not moving, there is going to be there is a force that's preventing it from moving, and that is the force of static friction. Remember, it prevents motion and is directed in it's directed opposite to the direction in which the object would move if no friction were present. So if you did not have this force, if this force were not there, then the box would have moved to the right if there was no friction. But the frictional force prevents it from moving to the right, so it must be acting to the left. And that's the force of static friction. We're going to use the symbol F sub S for that. And this again is another force exerted by the surface of the floor. So notice the surface of the floor exerts two forces, the normal force and the frictional force. So F sub S is the force of static friction. In terms of magnitudes, of course, we know that since the object is in equilibrium, in fact, in static equilibrium, the weight and the normal force are equal in magnitude. And also, the pushing force and the force of static friction are also equal in magnitude. And that's what prevents the object from accelerating. So in terms of magnitudes, the force of static friction is equal to the pushing force. Now, also note that if the pushing force goes to zero, if this person stops pushing, obviously now you cannot, if you remove this force, then you can't just have a force of static friction still acting on the box, because then the object would just spontaneously start moving to the left. It doesn't do that. So if the pushing force, if you remove the pushing force, then the force of static friction, then F sub S is also goes to zero. On the other hand, now this is something that you have experienced. Say you're trying to push a couch across a carpet, and you exert some force, and the couch is not moving. You can increase the force, and you find that, well, the couch still doesn't move. So you can change this pushing force, and you can push it harder, and still the couch doesn't move. Which means that as this increases, the force of static friction should also be increasing proportionally, since the object is not moving. So we also have this condition: as the pushing force, and we're talking here about magnitudes, increases, the force of static friction also increases. But eventually, if this person pushes the box hard enough, the object starts moving or accelerating, which says that, so eventually, if the pushing force is large enough, the box will start sliding, or as far as we're concerned, start accelerating or accelerating. Okay, and so, which means, so what that means is that the force of static friction must have a maximum value, because if the object starts sliding, it means that the pushing force now exceeds that maximum value for the force of static friction. Okay, so the maximum force of static friction, as it is called, the maximum force of static friction is, first of all, it's denoted by the symbol Fs max. Okay, and so we can summarize what I've just said up to now about this force of static friction by saying that the force of static friction can take any value between 0 and some maximum value. Okay. Now, what about this maximum force of static friction? What does that depend on? Well, as it turns out, experimentally, one finds that Fs max depends on two things. One, it depends on two factors. One, and this is kind of expected, it depends on the surfaces in contact. We know that you could have a box on a rough floor, and you have it takes less effort to get the box sliding, but if it takes more effort to get it sliding. But if it's a highly polished surface, then it takes less effort. So even for two similar surfaces, you can have different. I mean, you slightly change the surface, and you get the maximum force of static friction can change. So it definitely depends on the surfaces in contact. Second, as it turns out, it also depends on the normal force N acting on the object. And as it turns out, experimentally again, one can show that as the normal force increases, or if it's reduced, the maximum force of static friction correspondingly increases or decreases. Okay, so we can combine these two facts. So combining 1 and 2, we can write this mathematically as, we can say that the maximum force of static friction equals some constant, which I'm going to write it as mu sub s, times the normal force. So you read this as, this is the Greek letter mu, lowercase mu. So mu sub s times the normal force, and this, where in fact mu sub s, which is a constant, And also, if you look at this equation, Fs max is the maximum force of static friction. It has units of newtons. Normal force has a has units of newtons. So this constant is a dimensionless quantity, which means it has no units. So let me just mention that it's dimensionless. By dimensionless, I mean no unit. Okay, so it's a constant. It's called the coefficient of static friction. Coefficient of static friction, and it depends, like we said earlier, and depends on the surfaces in contact. Okay, and the text lists the coefficient of static friction for various surfaces, and here is the numbers, the coefficient of static friction, mu sub s, that we're looking at. So as you can see, just going down the list, rubber on concrete, that would be like a tire sliding on a road surface. The coefficient of static friction has the value 1. Steel on steel 0.8. Steel on steel lubricated, we expect it to be lower because it's easy to slide the surfaces against each other, and as you can see, it's 1/8 the value of when it is dry. Wood on wood, it's 0.5. Wood on snow, skis, if you think about skis on or a sled on snow, it's pretty low. Ice on ice, 0.1. So as you can see, it depends purely on the surfaces in contact. Okay, so that's the force of static friction. It can take any value ranging from 0, so it's not a constant force, up to some maximum value. And that maximum value for the force of static friction depends on the surfaces in contact, and it also depends on, which is characterized by this constant right here, and also the normal force acting on the object. Okay, so now, like we had mentioned earlier, there are two types of frictional forces. Then there is the force of kinetic friction. So again, back to this person pushing a box. Now suppose she started pushing. She's pushed it hard enough that the object starts sliding. So it's got some velocity. Now in this case, there is no, the force of static friction is now replaced by the force of kinetic friction. Another force of friction kicks in, and this kicks in when two surfaces are sliding. So when surfaces are sliding, it's a different type of frictional force, and it's called the force of kinetic friction. So once the once the box starts sliding on the floor, the force of static friction is replaced by the force of kinetic friction. The symbol for the force of kinetic friction is F sub k. As it turns out, the force of kinetic friction has a constant value, and the force of kinetic friction is less than the maximum force of static friction. Whoops, remove the vector sign there. It's magnitude wise, it has a lesser value. And this is again something that should sound reasonable, because suppose you're trying to drag a box across a floor. It takes a lot more effort to get the box moving, but once the object starts moving, if you want to keep it moving at a constant velocity, one thing you'll note is that you can kind of exert a lesser force and still get the box moving. Okay, so the force of kinetic friction has a value. Magnitude of the force of kinetic friction is less than the force of static friction. And here is the free body diagram that goes with it. And as you can see from this sketch, these two forces, if it's moving at a constant velocity, those two forces are the same, and these two forces have the same magnitude. But the important thing is and also the direction of the force of kinetic friction is opposite to the direction of the velocity. So that's pretty straightforward. If it's moving to the right, then the force of kinetic friction acting on the box is to the left. Now, as it turns out, the force of kinetic friction has a constant value, like I mentioned. And here again, the force of kinetic friction depends on the surfaces in contact and also on the normal force. Now this constant here is called, it's a different constant now for the two surfaces. Same two surfaces, you'll have a different constant called the coefficient of kinetic friction. That's the mu sub k that you see out here. So mu sub k is a constant called the coefficient of kinetic friction. Okay, and again, depends on the surfaces in contact and depends on the surfaces in contact. As you can see from this table out here, these are the coefficients of kinetic friction. Again, it is here again, it has a constant value. It's a dimensionless quantity. It has no units. And the other thing to note is for the same two surfaces, notice the coefficient of kinetic friction has a value less than the coefficient of static friction. And that makes sense. That is related to what I said before. Once you get two surfaces moving, once you get an object moving sliding on a surface, it takes less effort to keep it moving, and that's because the coefficient of kinetic friction has a smaller value, as you can compare if you compare these two. Okay. So if you want to summarize, here is a nice way of summarizing both the forces of friction, the force of static friction and the force of kinetic friction. What you've got a graph here on the x-axis, you've got to say it's the same situation where we had before, a person pushing on a box, but on the x-axis we are plotting the magnitude of the force exerted by the person, and on the y-axis you're plotting the frictional force. So initially, up to this point, the box is at rest. So as the person exerts a greater and greater force, as the force increases, the corresponding force of static friction also increases, because the object stays at rest and it's moving and it's not accelerating till a specific value is reached right here. At that point, you've reached the maximum force of static friction. That's this value here. After that point, the object starts moving. And now, if the person wants to keep the object moving at a constant velocity, she can get away by exerting a smaller force, because she just has to, the exerted force, applied force has to equal the force of kinetic friction. Okay, so let's look at an application of the frictional force, and this is one of the assigned problems, a homework problem. You've got two workers. two workers sliding a 300 kilogram crate across the floor. So the mass of the crate, M, is given, it's 300 kilograms. One worker pushes forward on the crate with a force of 380 newtons. So this person right here with the red shirt is pushing with a force of 380 newtons, while the other pulls in the same direction. So that picture, I've kind of pulled it out from the web, and I'm going to hide this little bit there. And just kind of, there we go. And that person is pushing on the, pulling on the crate with a pulling on a rope or exerting a force through a rope, and that force has a magnitude of 350 newtons. Both forces are horizontal. That's what this sketch shows you here. And the crate slides with a constant speed. So it's moving at a constant speed. What is the crate's coefficient of kinetic friction on the floor? Of course, here I've got a couch. Assume it is a crate that you have there. Okay. So the question that's being asked here is determine mu sub k, the coefficient of kinetic friction. You're told the pushing force, which I'm calling F here, is got a magnitude of 380 newtons, and the tension in the string has a magnitude, or on the rope has a magnitude of 350 newtons. Here is a free body diagram for the crate. What are the forces? There's the weight acting in the downward direction. There is work. I'm calling this person worker 1. Call this worker 1, and this is worker 2. Looks like they're twins. Anyway, so okay. So you've got the two workers. Okay, so these are the two forces in the horizontal direction, both horizontal. Okay, there's a normal force, and there is friction in this problem. And since the object or the crate is sliding, it's actually the force of kinetic friction. So you got to, know when to apply the, include the, you have to decide if it is the force of static friction or kinetic friction. And in this case, since the object is sliding, it is we are talking here of the force of kinetic friction. Okay, that tells you that it is the kinetic friction. Now, as we did in previous problems, the next step would be to resolve the forces into components. So you make this column right here, this table out here, and list all the forces, the weight, the force exerted by worker 1, the force exerted by worker 2, the force of kinetic friction, and the normal force. So there are 5 forces in all. But notice all the forces are either in the x or y direction, so it's pretty straightforward resolving them. I'm just going to write them down. That's 0 and negative mg. Pushing force is just plus F and 0. Tension is also plus T and 0. Force of kinetic friction, it's back this way. It's in the negative x direction. And we have an expression for the force of kinetic friction. That's the expression for the force of kinetic friction. So I'm going to write that down here. And since it's in the negative x direction, I'm going to write it as minus mu sub k times the normal force and 0, and this is 0 and plus n. Okay. Or maybe let me break this up rather than surprise you with that. Let's just put it this way. I'm going to write it as minus f sub k. And remember, where we already know something about f sub k is just mu sub k times the normal force. All magnitudes out there. Then from this point onward, the approach is pretty much the same in all the problems. Net force, write down the net force in the x direction. It's F plus T minus mu sub k times n. I've replaced F sub k by mu sub k times n. And the net force in the y direction is n minus mg. Again, applying Newton's second law. So we have Newton's second law, which says that net force in the x direction is mass times the acceleration in the x direction, and net force in the y direction is mass times the acceleration in the y direction. We definitely know the acceleration in the y direction is 0 because that crate is not leaving the floor or going down through the floor, so it's got no acceleration in the y direction. The acceleration in the x direction is also 0. And why? Because the crate is moving at because the crate moves at a constant velocity, and we are told that in the problem. And because it's moving at a constant velocity, the acceleration in the x direction is also 0. So that comes from that statement right there, constant speed. Well, now combining these, we have the equations. We got two equations now. We've got F plus T minus mu sub K times the normal force is equal to 0, the first equation, and N minus mg is equal to 0. That's the second equation. If you look at the first equation, that's what the unknown that we're trying to find. But if you look at that equation, we know these quantities. We don't know the normal force. But from this, the second equation, so from 2, we can solve for, but the fact is you've got two equations and two unknowns. The two unknowns being the normal force and the coefficient of kinetic friction. So from 2, we can solve for the normal force, N equals mg. Then we go ahead and plug in N in the first equation. I apologize if you can hear the lawnmower or riding mower in the background. So this is going to be F plus T minus mu sub K times mg is equal to 0, or mu sub K times m times g is equal to F plus T, and therefore mu sub K is F plus T over m times g, and whatever that comes out to be. Again, remember, the coefficient of kinetic friction and the coefficient of static friction are both dimensionless constants. There are no units attached to them.